Hello everyone. I'll introduce myself. I'm Xiao from the University of Edinburgh. So today I'm going to introduce you the standard disentangling models, including VAE, GANs, and normalizing flows, and also the content style disentanglement. So Pedro just introduced the fundamentals of the theory part of representation learning of like disentanglement. So what about the models? Well, when we talk about disentanglement, the target is how to learn a good disentangled representation. That in this case we will have an encoder to encode the original data to this latent space. Then we can consider a simple view or simple analysis behind this. Usually, we assume each dimension of this latent representation is uncorrelated to each other. But actually, this uncorrelation, there are multiple different interpretations about like what kind of unrelated means. So also ideally, just like the question someone asked about the supervised or unsupervised. Ideally, we want to do this unsupervised because usually we don't have enough. Sometimes we don't have the labeled generating factors behind this. So the simple idea is we can have an encoder, also a decoder, to first encode the data to this latent representation, and then we can decode the latent representation to the original input data. So this strategy is encoding and decoding from like autoencoder, and we can do this to learn the latent representation in an unsupervised manner. So this is the reason why we have this encoder-decoder structure. So overall, in considering this encoder and decoder structure, we have a couple of different frameworks or models to achieve disentanglement. The first one, as you can see here, is VAE, and then we have generative adversarial networks. Also, more recently, the normalizing flows, and finally, the content style disentanglement. So then, considering those frameworks, how do we learn a good representation? Is the following question. Well, in variational autoencoder, so I will first talk about the fundamentals of VAE and then how VAE is used to learn the representations. In VAE, usually you assume a specific prior on the latent space. So the latent representation follows a prior distribution. So you can see the p theta data here. You can see we have the encoding x to z and decoding path z to x. Z here follows a prior distribution. Usually it's normal distribution, a Gaussian distribution with zero mean and variance 1. And so we're encoding x to z, we can also decode it. So here we have the posterior distribution of z, and also the likelihood of x giving z. And in VAE, there are two terms in the learning objective. The first term is we want to force the latent representation to follow the prior distribution. And this means we want to force the posterior distribution to be identical or similar to the prior distribution. So we use KL divergence to force it. And the second term is to decode the image, to reconstruct the image to be similar to the original ones. So this is the overall learning objective of VAEs. And this is actually called evidence lower bound. In aspect of information theory, it's actually the approximation of mutual information between the latent space and the input image. So about VAE, so the tricky part is the KL divergence term here. Usually it's very hard to directly calculate the KL divergence between two distributions. And especially in this case, we don't have a form of the poster distribution. So in VAE, they do the reparameterization trick. So they do not encode the latent representation directly. They rather encode the mean and the variance of the latent representation. And because the prior distribution is a normal distribution, we have the function of the distribution. So here easily we can calculate this KL divergence term by using this trick. Then when we talk about disentanglement in VAE, actually the story starts from beta VAE. Beta VAE is quite simple comparing to the original VAE. You can see they only insert one term beta here. This actually hyperparameter, right? In the KL divergence term. Actually, when beta is very large, the encoder distribution, the poster distribution, is forced to better match the prior distribution. And in this case, actually, it additionally constrains the capacity of the latent bottleneck. So it's like the image and also the latent space and the image. So the information flows like, go to the larger capacity, then go to the bottleneck, a smaller capacity, and then go to the image, larger capacity again. So it's like a bottleneck. And this actually encourages the encoder to learn a disentangled representation for the data. Especially when beta is very large, each dimension of the latent representation Z is independent or uncorrelated with each other. So you can see the results here. They can capture the position factor, the horizontal and the vertical positions, and the scale and rotations and angles of as the generating factors. This is actually quite impressive. And then many papers were proposed to somehow improve the disentanglement using VAE structure. But in beta VAE, there is a problem between the reconstruction quality and also the level of disentanglement. So why? Because when the capacity of the latent bottleneck is very low, actually we don't have much information flows from that bottleneck. So when you reconstruct like little information to a lot of information, actually the prediction is not very accurate. This makes the reconstructed image to be blurry. And so they consider this KL divergence term as the capacity, and then the group progressively increase the bottleneck capacity by controlling this C parameter. And this is called annealed VAE. And at the training of the start, of the beginning, C is set as 0, and then it's progressively increased to increase the capacity. And at the same time, we can also learn a good representation. So we have a comprehensive review on VAE in our accompanying material, the paper of this tutorial. So you can check it a bit for more interesting VAE models. So the next one is generative adversarial networks. So when we talk about GAN, it's quite famous, and I guess a lot of you have heard of it before. So generative GANs actually do not have a typical encoder. They have a generator, and they rather have a discriminator. So the structure of GANs are quite simple. The generator inputting some random noise, then generate some output samples, and then the discriminator is trained to tell if the input is from the real data distribution or generated by the generator. And also the generator is trained to make the discriminator to cannot tell if it's from real distribution or from the generator. So it's like a adversarial GAN between the generator and discriminator. And the variant of GANs is one of the variants of GANs is conditional GAN. So simply we can add a condition here to control what kind of output we want the generator to generate. For example, for the dataset MNIST, we want to generate different digits different numbers, we can control it here by telling the generator, for example, to generate digit 5. Yeah, so so we can check a bit the previous Mikai 2019 tutorial on GANs. Also, they have I think they have a review paper on this. So what about disentanglement in GANs? Again, the story starts from InfoGAN, so information GAN. So the intuition of InfoGAN is simple. It's based on conditional GAN. So we have a condition here to the generator. We want the generator to generate based on this condition. But there is a problem. So usually the generator just ignore the condition if there is no any constraint on the output on the discriminator. So how to solve this problem? The theoretical intuition of this problem behind is we actually want to maximize the entropy or mutual information between the condition and the output, such that the generator will not simply ignore the condition. And InfoGAN do this by introducing an auxiliary network, and they share the weights between that network and the discriminator. So in this case, in InfoGAN, the discriminator will also predict the condition. So they have a condition here, and the discriminator predict the condition, also tell if it's real or fake. And when we minimize the distance between this condition and also the predict condition, we actually maximize the entropy between condition and the output. You can check InfoGAN for more theoretical analysis. And so that's InfoGAN. So that's disentanglement with GANs. And when we talk about GANs, we certainly want to check a bit about more advanced GANs like StyleGAN. So it's quite popular in GANs because it can generate a very high quality images. And so about StyleGAN, it's quite simple. You can see here, this is the traditional structure of GANs. So we have the latent space side, and we upsample the latent representation to an image. But for StyleGAN, it's slightly different. First of all, it maps the input that here, the latent representation, to an intermediate latent space here, omega or W. So then it controls the generator. So this is the generator part. Controls the generator with the mapped latent representation by inject by inject this representation to all the convolutional layers using adaptive instance normalization. And then the Gaussian noise here is added after each convolution before evaluating the non-linearity. And using this model, this noise can control the texture, the details of the generated images. And then they proposed the StyleGAN too, because in the normalization layer here introduced some normalization artifacts, the blobs here, you can see. And they proposed the improved version of the normalization layers. So with this more advanced GAN, the StyleGAN, how can we do to achieve disentanglement? Well, it's relatively quite simple. We can just from GAN to InfoGAN, from StyleGAN to InfoStyleGAN. So it's quite simple. And you can see this is the StyleGAN. They just added this factor code. This factor code is the condition we just mentioned before. It actually can be someone mentioned before, like the facial expression and also the sex, the gender information. And then they have the discriminator here predict the factor code. So you can say when they minimize the distance between the factor code and predict ones, they can maximize the mutual information between this representation and the output image. So it's quite simple, and you can see they can capture they can really learn the generating factors like the glosses, open mouthes, etc. So you can see here from without glosses to with glosses, quite impressive. And finally, we just talked about VAE and GANs and their actually not invertible. So when you have an image, you encode it to the latent space. Actually, you do sampling, so it's not one-to-one mapping. So flow-based models, they allow us to estimate exact likelihood of the data, and when we have the prior distribution of the latent space, and also we can know the reverse direction. This is the advantage of normalizing flow. So normalizing flow is defined as this. We have the transformation here, and we have the latent representation side, and we can predict the data. And so it also follows the encoder-decoder structure. So you can see here, we have two transformations. One is the original transformation, and the other one is the inverse of the transformation. So we can predict the distribution of the data by only using the transformations, and also the distribution of the prior distribution of the latent space. There are some requirements for flow-based models. The transformations, actually, the transformation and the inverted transformation should be differentiable and, of course, invertible. So this actually makes flow-based models harder to design. So you can see a couple of samples here generated by normalizing flows using glowing. Also pretty high quality. And this is actually 1024 times 1024. So what about disentanglement in normalizing flows? Well, I will provide two examples here. The first one is in computer vision. So you can see here they have an encoder, they have a decoder. So it's just the autoencoder structure. And this side, if there's no any constraint, it's just the just the latent space of autoencoder. There is no disentanglement here. So they actually further encode this latent representation side to interpretable representations with normalizing flows. So here's the transformation, here's the inverse of the transformation. So you can see these interpretable representations are actually disentangled. So this means we disentangle the latent space from entangled space to disentangled space. And this can let us to manipulate the output images by manipulating the disentangled representations. And you can see here the change in the appearance, also somehow the content, the spatial information. And the other one is in medical image segmentation. In medical domain. So you can see here they design a multi-scale flow-based model for correlated spatial features disentanglement. So they assume they have the paired seed images. And this one is without tumor, this one with tumor. And so they can extract the correlated information at the loss scale and extract the non-uncorrelated information between the two images in other scales. So in this case, they can separate out the correlated information and the uncorrelated information. So this is equivalent to disentangle those information. Yeah, I just talked about the VAEs, GANs, and the normalizing flows. What about the limitations or main issues of those models? I mean, I just talked about how good they are, how theoretically guaranteed that they can extract the disentangled representations, how high quality they can generate. So for VAEs, actually VAEs suffer from achievability elbow because there is a trade-off between the level of disentanglement and also the reconstruction quality. This means VAEs usually create results that are quite blurry. Although VAEs have nice theoretical results, but actually they're usually validated on toy or synthetic datasets. And for GANs, yeah, it's notorious. The training stability of GANs is still a problem. And in particular, it's quite hard to enforce equivalence on the latent factors of GANs because we directly sample from prior distributions, like Gaussian distribution. And this means we cannot use the factors directly on equivalent tasks. It's like medical image segmentation, right? Registration. So normalizing flows, although we can have exact likelihood estimate, we can have invertible transformation, but it's harder to train because you remember the requirements of normalizing flows. The transformations should be invertible, should be invertible, and should be differentiable. So usually there are some requirements on the model design, and this means usually we have heavier model with more weights, so it's harder to train. Overall, all those models, we don't have a widely agreed metrics on the disentanglement, like in VAEs, the uncorrelation in GANs, maybe just somehow independence. And maybe we can use GAN inversion to find, but no widely defined disentanglement definitions, and also the metrics for all the models. More importantly, we cannot directly use the representations learned from those models for downstream tasks. Yeah. So why we have those limitations and issues? Well, the whole story is about biases. Well, we all know there are three different kinds of biases. Data biases, inductive bias, and also learning biases. So inductive biases here, you can simply imagine it as model design biases. I mean, it's a simpler definition like that. So you see in VAEs or GANs, we have the data bias like MNIST. So for example, MNIST, if we design a disentangled representation, there will be like 10 discrete representation dimensions to represent the 10 digits. So this means based on the dataset biases, we need to design specific inductive biases and also learning biases to achieve certain disentanglement. So you can see here, all the models I just introduced, they introduce different biases because of the different dataset biases. But the fundamental question is, are we capturing the real world dataset biases? We all know medical applications, they are somehow more practical compared to computer vision tasks. So this is the fundamental question. And you see here, I'll give an example, like a lot of computer vision datasets, they're actually synthetic. So the ground truth factors behind those images or behind those data, they are somehow synthetic, they're simulated, they're not the real world generating factors. And you can see, although we have a more advanced real world 3D dataset, like in this paper, they have 7 factors, but still it's synthetic. It's not realistic. It's still somehow a toy dataset. So what about real world biases? Well, it comes to the story of the content that still disentangled. Because imagine in the real world, the simplest dataset biases, when you observe, when you go to see a mountain at the day and the night, the mountain is the mountain, right? It's always there. But at day and the night, the modality, the intensity, the imaging statistics, they're different. This means this dataset bias, we can take advantage of this. So we can design some inductive biases to reflect such dataset biases, such real-world dataset biases. And this is the motivation of content still disentanglement. The biases, the dataset bias here is quite simple. We know the neighboring pixels of images, right? They're correlated. They have some spatial correlation. We can convert it to design biases or inductive biases by using convolutional neural networks. And this is the content still disentanglement. What content still disentanglement does. So you can see here, for example, in still transfer, we can change the still, but we can still keep the content, right? So For content style disentanglement, there are some remarks. It comes from it's not first to consider to separate the content and the imaging intensity, imaging statistics, or the style representation. So actually in texture transfer or style transfer, image transfer, they somehow have this equivariant framework. Although in those models, they do not explicitly extract the disentangled style, they have the content, just like the example I gave about the style transfer. They can keep the content but change the style. So this actually establishes image-to-image translation to keep the content and change the images into different domains. And it actually sparked some new ideas and directions. So also, you see the spatial content here actually enables the exploitation of equivalence property. It keeps the spatial correlation, spatial structure of the image. Also, using the style, actually, we can explore the invariance of some design operators. So about the content disentanglement, well, I'll introduce somehow start from the image-to-image translation. Taking the advantage of content cycle GAN, we can do it in an unsupervised way. You see here, we have some labels, like segmentation labels, and those are the practical real-world images. So we can translate them to the images. So you see from the one domain to other domain, the content are somehow kept and the style are changed, but they actually don't extract the style explicitly. So, but the importance from image-to-image translation is we can somehow use this to achieve unsupervised learning or somehow self-supervision. Yeah, so based on the image-to-image translation, we can consider the segmentation, like in medical image segmentation. We can consider the segmentation mask as a domain. And then or we can consider as a latent space. So this means the representations, the spatial content representations, it can be multi-class, it can be semantic, it can be a binary. So it depends on the design. And then we can use the content representation to other equivalent tasks like image translation, image registration, image segmentation. Yeah, so taking the advantage of reconstruction, like image-to-image translation, we can learn this content representation in an unsupervised way or the semi-supervised way. I mean, just like the question Zikang mentioned, can we do it totally in an unsupervised manner? So you see, the case here is if you don't know what the content you want, no supervision at all, actually we cannot learn very good content. So we have to give it some supervision. Like here we use the segmentation. We can use the segmentation mask as the supervision. So, but we can still use the unsupervised data, the unlabeled data here. Actually, so you can see here, if we just use the technique from image-to-image translation, we don't have the style, we only have the content. But the problem is many images, they can have the same content, but they don't have the same imaging statistics. Like this image and this image, they have the same content. So this means we need to encode the style representation with this with a auxiliary or alternative encoder to encode the imaging features. So this is the content style disentanglement framework. We use the decoder to combine the imaging features and also the anatomical features or content representations or still representations to reconstruct the image. Also, we can use some supervision to the content representation. So there are two questions here. One question is, can we give like less supervision or weaker supervision to learn a good content? This is the fundamental question. You can somehow find the answer in the later session about challenges and opportunities in disentanglement. And the second question is, how can we design the decoder? Or how can I build this, even when considering your own tasks at hand? Yeah, so for the how to build this, Spiros will introduce you later about the building blocks, also how to use some metrics to measure the disentanglement. Finally, to recap, so I discussed the three standard disentanglement models, VAEs, GANs, and normalizing flows. So there are some limitations and main issues of those models, mainly based on data biases of the synthetic or toy data set. For more real-world data set, we can consider content as still disentanglement. Yeah. So that's this part.
So I want to take it from here.
Yeah. So I will stop sharing.
Okay. I guess you can see my screen.
Yes.
Nice. Hello everyone. My name is Spiridon Thermos. You can call me Spiros. And now we're going to discuss, after detailing the fundamental concepts of disentanglement, now we proceed to discuss about the building blocks or layers and modules that encourage disentanglement and are used in disentanglement-based architectures that you saw earlier, and some more complex architectures that we're going to analyze in the next session of the applications. Also, as we know that in order to understand disentanglement and build models that improve the way that we disentangle, we need to quantify how disentangling are the encoded representations. So we are going to also do a quick overview of the existing metrics. All right, regarding the building blocks. So if you want, the first thing that it's very helpful to do is combine different inputs, so combine different encoded representations. And the most naive method is to encode different attributes that have been encoded into different latent vectors, and combine them in order to reconstruct the input or generate a new input. So concatenation of two vectors. The problem is that this is inefficient if we don't have two vectors, but we have two or more tensor representation of any dimensionality. So that's one problem of concatenation. Another building tool that's mostly related with vector-based encoding is the average pooling. That is a common trick that is used to usually to extract the style representation of the input, as it encodes the global mean statistics and removes any spatial correlation. Now the content side, another tool is Campbell softmax. So it's a differentiable variation of typical softmax, so it can be used as an intermediate layer in our model. We can backpropagate the gradient. So assuming that we have a spatial content, we can benefit from gamble softmax as it can lead, if it's applied in a channel-wise fashion, it can lead to semantic representation. In general, we can benefit from discretizing the encoded continuous information. Right. The next one. Next, we're going to talk about normalization layers. Batch normalization is the most widely known one, as we know that it significantly eases the training of feed-forward networks, and it was originally designed to accelerate training of discriminative networks, but was also used very effectively into generative modeling in general, as it has been proven to alleviate domain shifts. Now, batch normalization has two affine parameters, gamma and beta, that enable that can shift and scale our representation. They're both learnable and they are learned from our data. So batch normalization is computed across the batch and also across the spatial dimensions. Another variation, more recent, is instance normalization. You can think of it as using batch normalization with batch size equal to 1. It was originally introduced in style transfer architectures, as it has been proven to remove contrast-related information from each instance. So we compute the mean and the standard deviation across spatial dimensions independently for each sample, not across multiple samples. So we know that gamma and beta can help either computed in a whole batch or in a single sample, but is there any way that we can make them conditional? Can we make them to adapt into different styles, for example? So the answer is yes. We have two very well-known approaches, the feature-wise linear modulation, and the adaptive instance normalization ones. As you can see, the generic expression of shifting, scaling with gamma and shifting with beta. So both of them are a conditional extension of the batch of instance normalization. So the affine parameters here, are replaced by the mean and the variance of another network, let's say a multi-layer perceptron that encodes the style of the input. Similar to the instance normalization, the statistics are computed along the spatial dimensions and not only, and not across the whole batch. The top two applications of film and undying, one is film is used in BQA, and undying is mostly used in style transfer networks. We use them to combine, to re-entangle the disentangled content and style representations into content-style disentanglement architectures. We're going to see a lot of examples like this in the application part. All right. Sorry. Instead of another conditional approach, but instead of computing using the MLP and applying this gamma and beta as vectors, is using the spatial adaptive denormalization layer network called SPADE, which uses segmentation maps, or in general semantic maps, as a conditioning input. So here we, instead of scaling a vector to a tensor, now we scale a tensor scales the vector that comes as input. So the scale and shift factors are actual tensors computed with the help of some convolutional layers, and enforce some spatial manipulation. It's the same logic. We have one tensor for the gamma and one tensor for the beta hyperparameters, and this has been used mostly in image synthesis models. Now, some other building tools, the most frequently used in terms of encoders are frequency decomposition methods like DCT or the fast Fourier transform that extract the domain invariant and domain specific frequency components. Regarding the latent space, you will see the gradient reversal layer, GRL, that's placed usually after feature extraction layers in order to force domain invariant features, and also Gaussian distribution prior or some other priors. Usually it's the Gaussian distribution prior, so we learn a representation and we try to enforce that the distribution of this representation matches the one of the Gaussian isotropic Gaussian distribution. And also regarding the learning setups, we have the cycle consistency losses that again we're going to see some very good examples in the applications later, and the latent regression that ensures that the decoder does not ignore any latent pattern. Now, okay, we're done with the building blocks, or at least the most widely used building blocks. Now we want to briefly report the most popular disentanglement metrics, and we're going to split them into two categories. The first category is the metrics that are in the field of single vector latent variable encoding, and the second category is about the representations encoded into two or more latent variables of the same or different, and that's the key here, or different dimensionality. Okay, regarding the first category, the single latent variables, as I said earlier, they're vector-based, and what we want to investigate here is the relations among different dimensions of the same vector. This category consists of both qualitative and quantitative methods for measuring disentanglement. So the qualitative one is the value traversal. So here we traverse a single latent dimension that alters the reconstructed image by a single aspect. Practically, there are linear interpolations that allow us to perform walks in nonlinear data manifolds and interpret the results in terms of the type of variation that we control, and does not require any ground truth. So about the quantitative part, okay, considerable effort has been spent to qualitatively evaluate vector representations. You can see three of the most desired attributes that we want to measure: modularity, completeness, and linear separability. We want our representation to be modular, so we measure if its dimension depends on at most one factor of variation. We want the representation to be complete. So here there are metrics that penalize a factor of variation for being captured by multiple codes, multiple different dimensions. All the linear separability has been introduced from the StyleGAN that Xiao discussed earlier. So the assumption here is that if a latent space is sufficiently disentangled, then it should be possible to find direction vectors that consistently correspond to individual factors of variation. So assuming that we have two binary factors of variation, we can always find and draw a linear hyperplane to separate them. Right. So we talked, we talked about the existing metrics, but there is a problem here. So there is no widely adapted metric. So many metrics, there exist many metrics, but there is no like one or two metrics that are widely applied to that you can see to every paper. And this is a serious discussion in the disentanglement community. And the problem, there are several papers that I plan to start to evaluate if we indeed measure disentanglement. And also the question here is that can these metrics evaluate the models trained in the real world data? Because usually most papers use toy data sets, and the metrics struggle to perform the same way in real world data. All right. So we discussed about single latent variables. Now about single latent variables and mostly vector-based. Now we're talking about two or more latent variables that can have different dimensionality. So the previous metrics cannot be used directly in content style disentanglement, as they rely on having ground truth factors, and they assume the vector-based setup. That's why there's a recent work that tries to measure, instead of measuring the disentanglement of the different dimensions inside the representation, they try to evaluate how disentangled are two different representations. Either they are vectors or vectors and tensors. So we measure the cross variable disentanglement. And they measure it in terms of how uncorrelated the two different representations are and how informative each one is compared to the input. Okay, so okay with the theory, but this tutorial we also have some useful tips for you regarding the vector-based disentanglement approach and setup. There is a very well-known library, disentanglement lib, that you can check on GitHub. There is a link below the image. You can find most metrics regarding the single vector-based latent space, and also for the content style, disentanglement. You can also check this library. Again, the link is under the image. Okay, to recap, we checked very quickly the building blocks for disentanglement and also the two categories of the metrics. After the short Q&A and after this Q&A session and the short break, we're going to check some applications of disentanglement, starting with computer vision, moving to the medical image analysis that's the most relevant with MICAI, and continue with another relevant part, the electronic health records. So I would like to stop here, and if you have any questions, you can request to unmute the microphone or to type it in the chat, and a colleague of mine will inform me. Okay, so the first question is on you, I guess.
Mm-hmm. So could you please explain the meaning of the attitude in the first figure in the slide normalizing flows for disentanglement? Does each position of the attitude have specific meanings? Like the first value of the attitude means gender. Yeah, so in that case, it's quite similar to VAEs. You can check the paper actually for more details. But in general sense, some dimensions or one dimension can mean specific things. I can share the paper to you actually. The second question is what is the advantage of normalizing flows compared to VAEs and GANs in medical imaging? Can you give an example where it has advantage? So when we talk about the advantage of these advantages of each models, I think for normalizing flows, usually the advantage people talk about normalizing flow is it's invertible, so you have more control to your latent space, and you have more control to your transformations. So this is somehow like the like in VAEs, you don't know if you don't have like any supervision or any constraint, you don't know the first dimension of the latent space. What the first dimension of the latent space correlates to? Is it correlates? Does it correlate to gender? Does it correlate to age? You don't know that. After you train a VAE, you do the latent traversal, you will know that. But for flow-based models, disentanglement in flows, it's more controllable because you have one-to-one mapping. You know the transformation. You even know the inverted transformation. Yes, so I think that's a big advantage in terms of disentanglement or medical imaging. But I think it's there is open, there'll be a huge open discussion about the disadvantages and advantages between VAEs, GANs, and normalizing flows, even the energy-based models. Yeah.
Yeah, and I also guess that for now we don't have many papers working applying that to medical imaging, and I don't know, it's not very clear that in terms of image quality and it's worth using generative models based on normalizing flows. But there is some very interesting work on that recently.
Yeah, so there's a question about building blocks, Spiro. So
Yes.
Can their choice have an impact to interpretability of synthesized medical images? Some of them produce more artifacts than others.
Yes, that's a very good question. In general, building blocks, the choice of the correct building blocks is crucial, as it's the same question as asking, do the different hyperparameters affect how you learn your what your model actually learns? So the answer is yes. I'm not sure if you have something specific in mind about inserting artifacts in the generated or the reconstructed model. But in general, a very quick example that we will see it in the application section is that, for example, we saw that the Gamble softmax produces binary softmax in general produces a binary representation. So a binary representation means that I know that in a specific channel either there is something of the content part, or there is not a content part. It's not spread across channels. It's only in one channel. So this means that you encode a semantic content. So this is something that can be very helpful if you're using your content for segmentation, or not helpful at all if you're just re-entangling the content in the decoder part. It depends on the task, on the parallel task that you need, and it depends about how you're going to exploit the encoded representation. Either it's vector or tensor based. Okay, there's another question. You mentioned without supervision, no disentanglement, maybe a bit exaggerated. Can you elaborate how the presented models, for example, VAE or normalizing flows, use supervision for disentanglement? So do you want to answer this? I can, if you want. So let me do that very quickly. Yes, there has been the discussion about this unsupervised disentanglement, and there are proofs through heavy experimentation that unsupervised disentanglement does not exist. So you always need to introduce some bias either from the data, okay, or from the model, or from the learning objective, so the learning setup. The supervision is one of the three possible biases. So even if you don't use the supervision as a bias, maybe you have a heavily biased model, heavily based design. So implicitly, you give some supervision through your design. The example with the softmax in the content part, so making it binary, coding a binary content, is is an example of this part, or using contrastive learning only on your encoded style in a vector is a learning setup bias. About
also one of the papers from Locatello, they specifically enforce specific points in the latent to be equivalent to certain generating factors. So and other weak types of supervision. I think there is one of the papers in Disentanglement Normalizing Flows. They use some kind of contrastive. It's kind of a contrastive learning approach where they force latents of similar images to be similar, given for a given attribute, right? So it is a supervision in form of a contrastive supervision. But yeah, there are a few different ways of reinforcing that.
I only wanted to add, just so we can allow a couple of minutes for the people that present next to rest. But just to answer to Rasha, I think, in my view, even in very simple linear models, you can easily tell, you can find, let's say, disentangled representation like in ICA, but then any simple rotation of that matrix will still allow you to be a disentangled representation. And it also means that you can have a fully a case where, although you think you're disentangling, it doesn't mean that two of your sources are actually not entangled, and you're not able to break them down even further. And that leads to the issues when you have the data being actually correlated and you're not observing all the possible combinations of the generating factors. So overall, I think, yes, it's exaggerated, but it's for the point of view of acting as a lesson, in the sense that don't hope for miracles. You will have to spend effort, either effort in some annotation, or either effort in designing the model, or either effort in designing losses, or effort in designing other sort of inductive biases. So I think that's why we wanted to exaggerate as a way. It doesn't come for free.
Yeah, and I think the supervision here, it's not simply the labels. It's like in general sense, the supervision, the pranology, expranology of the data.
Yeah, I guess supervision means like a human involvement. Let's call it like that. Yes. Whether that human provides labels, or that human designs the model, or that humans incorporates any sort of prior into that. Okay.
Yeah.
So I think because we have told our guest speakers to come in 1 hour, so maybe it's good that we take a shorter break of 5 minutes, and then we quickly move to the next session. Is that okay, guys? Spiro,
yes.
Alison, are you okay with that?
Of course. We have a couple of unanswered questions, so guys, hopefully we're going to cover you with the application part and the comments that we're going to do, because both of them are very related to what is going to be presented.
Yeah, I think we have not only answered Bella's question, right?
And also,
no, Rasha.
Only Bella. Yeah, indeed. Rasha was.
As you take a rest, I may answer that. Okay, it's fine.
Okay, excellent.
I may tap it up, but as you get some water, it should be okay.
Maybe Rasha's question. Did you answer?
I answered Russell's question.
Okay.
I think. I mean, it's exactly to the point of what supervision means. And as you rightly said, supervision can be anything. In fact, in SDNet, we did use auxiliary regression tasks for obtaining supervision. In the work with Gabriele, we used the temporal correlation as a way of self-supervision. So yes, definitely you will get you will get benefit from using additional tasks. Now, in terms of you will get a different level of disentanglement, that's an interesting question. I think one thing that Spiros did not highlight is one of the needs of why we need metrics is the ways of comparing models. And you know, you can design different architectures, you can design different models. How do you pick the right one? Francesco Locatello's slides will also, in the discussion at the end, will also mention that. What is the right bias? What is the right model? So we cannot, I think it's an interesting question to see which one is the right combination of things, but at least now we have metrics to at least help us quantitatively define that. Well, let me find Bella's question, and if I find Bella, if we're only testing robust segmentation results, is there a benefit of using common style disentanglement compared to standard segmentation, UNest-based architectures? That's a very interesting question. So if you work in the limit of infinite data, you don't need content style disentanglement. If you are like us, that we believe that no data are enough, because you're not going to have all the possible combinations of generating factors, there is a benefit of using disentanglement. And in fact, as you will see later in the applications, you will see that disentanglement also helps with domain generalization, based on a recent work of Shao, or also the ability to create synthetically new anatomies as a recent work of Spiros. So there are still benefits of having the idea of what a latent representation means, which you don't get with a unit. With a unit, it's kind of like a black box with all these residual skips. So we still believe that representations are useful. So you can imagine if you train a very good segmentation model with a unit, then what can you do with it if you change task or if you change modality? So we still believe that having representations are useful no matter what. I hope Bella did not leave. And okay, yes, she heard that. Okay.
Well, yeah, later in the last session, actually, Qidou will talk about domain generalization and disentanglement. So follow up.
Yeah. We throw all the nice links so we keep people so not to leave. So we don't tell you everything.
Yeah.
It's gonna come.
Another interesting application that we saw in Gabriele's work is test time training that also helps in robustness and generalization. When you have these architectures where you have this multitasking, a way of improving your latent space at test time, you can basically improve segmentation, for example, during test time, doing like this fine tuning over one image. And this is something that is there are a few papers on that recently, and I think that's a very exciting area.
Indeed.